Hello everyone, welcome to this second chapter. So the first chapter was on difference of Picard ratio extension. So we have seen that given a difference equation, there exists Picard ratio extension. So basically it's a set where the solution lives. And today we are going to see the definition of the difference Galois group. So it will be a group that we attach to the equation and that helps you to understand what are the algebraic relations between the solution. So let me give the picture. So of one side you have the Galois theory, and from the other side you have the difference Galois theory. So from one side the main object is a polynomial equation, and from the other side the main object is a difference equation. So in Galois theory you have the notion of splitting field. So it's a field that contains a solution. Here it was a notion of Picard extension. So we have seen that it's not generally a field. The main reason of that is that you caution by a maximal sigma ideal, which is not necessarily a maximal ideal. So you may add some zero divisors. And so you have the notion of the Galois group, which is just the automorphism of k leaving little k invariant. And here you have an additional structure of sigma. So when you define the Galois group, so of course you want to consider, I will give a precise definition of all this object later, don't worry. I just gave a first picture. So you want to consider ring automorphism that leaves k invariant, and you want an additional structure. You want the commutation with your automorphism sigma. And the goal of the Galois group is to measure the algebraic relation between solutions. So bigger is this group and less algebraic relation you have among the solution. So let me start with some definition and first properties. So let K sigma difference field as in the previous chapter, and assume that C, so the field of constants, is algebraically closed. Okay? So let me assume that so it's a good framework to have the Picard ratio theory, because in that case there is a uniqueness of the Picard ratio extension, and you will see that a lot of things works. So let R-tilde be the Picard ratio extension. And we have seen that the field of constants of R tilde is the same as the field of constants of C, and two fundamental solutions, U and V, differ by an element of GLN of C. So in other words, sorry. If you take U times V minus 1, you are in GLN of C. So let me define the different Galois group. So the PV group. So I will make a slight abuse of notation because there will be no Galois group. So I will take the same notation as for the Galois group. Is the group of ring automorphism of R tilde leaving K invariant and commuting with sigma. We have a first result of structure. So let U be a fundamental solution. So we have an injective group morphism. So this group, this morphism that I will call rho U maps the Galois group to GLN of something I will say in a few seconds, and to Psi you map U minus 1 Psi of U. So obviously it's a matrix, and in fact it's a matrix with constant coefficient, and this matrix I will call with bracket. So the second thing is that if we change the fundamental solution, we conjugate the representation. So a map of this thing is called a representation, and if you change the fundamental solution, you just conjugate the representation. So a Galois group may be seen as a group of constant matrices up to a conjugation. So this result is not very complicated. The fact that Psi commutes with sigma implies that so you can apply the both things to U. And on the left side, so you have, you have a Psi of AU So it's equals to psi of A, psi of U. And since phi leaves the entries of A invariant, you find so sorry, it's on the other side. So it's sigma of psi of AU, which equals to you separate and then no, sorry. I just confused between the two. So sigma of U equals A times U. So it's really on this side. So okay, and then so you use the fact that yeah, we are done. So it's phi of A times psi of U. And then I use the fact that psi leaves the entries of A invariant. So okay, so it implies that phi of U is a fundamental solution. So it means that there exists C tilde having coefficient in C such that psi of U equals U times C tilde. So it implies what I said, meaning that U minus 1 CU as a constant coefficient. So okay, so now if I change my fundamental solution, so and I consider V minus 1 C of V, so it's equals to C minus 1 U minus 1 psi of U psi of C tilde, and again psi leaves C tilde invariant, so everything works. So if you change the fundamental solution, you just conjugate the equation. So let me make a remark. So from now, we might identify, sorry. We might identify the Galois group with its image inside GL. Okay, but you can say something more. You can say something more. In fact, it has a structure of an algebraic group. So let me define what is an algebraic group. So we say that J Jn of C, that belongs to Jn of C is an algebraic group if J is a group and there exists P1 until Pk so it's n square indeterminate, so E and G are between 1 and n, such that M belongs to J if and only if it satisfies a certain number of algebraic equations. So for example, so J equals SLN of C is an algebraic group. So J is just the matrices. So SLN is the group, of course, and you have the functional equation. So you really need two things. You need to be a group, and you need to be solution of algebraic equation. So there are not so many groups. So exercise. Say if the following are algebraic group. If yes, say what is the algebraic equation. So the first example is nilpotent upper triangular matrices. SON triangular matrices diagonal matrices unipotent matrices and last one matrix with integer eigenvalues. And so now I'm ready to prove and to state maybe the main theorem of difference Galois theorem. So the Galois group is an algebraic subgroup of Gln of C. So let me prove in the case n equals 2. So it's just because the notation are more simple. the proof passed word by word for our arbitrary equation. So it's just to help to understand. So let's consider the Picard ratio extension. So I remind that Z will be a matrix with indeterminate coefficients. That is solution of the equation. And I the maximal sigma ideals. So let me start with a remark. So let me take constant matrices. So you may make act on the fundamental matrices via the following action. So you don't have many solution possibilities. So you just multiply to the right by the matrix. And let's remark that J belongs to the Galois group if and only if J maps the ideals E to itself. So we are looking at automorphism, at matrices that preserve the ideals that define. And we will see that I is very closely related to the algebraic relation. So I remind that it's finitely generated. So it's generated by ideals P1 Pi, and I call M the maximum of the degree of the Pi, and let me call W. It's the K vector space of K of ZEG of degree less than M. And let Qi a basis of this vector space that we intersect, and with the ideal, and I extend to a basis. So this time it belongs to B of W. So now let me see the action of the Galois group on an element. So I will remind so it was the action of the right multiplication. So it's the sum of polynomial of this form. And the PHG so from one side, you just separate the indeterminates A, B, C, and D, the coefficient of the matrix A, B, C, and D, and so since it acts, so it's not PG, it's QG, and since it acts, you belongs to W. So okay, but we can do better. So the fact that J leaves E invariant implies that PEG equals 0 for all E that belongs to A and J that belongs to the complementary of A. So of course, if you want to stay in I, you need that the QG that does not belong to I are 0. Okay. So you start to see that you have a structure of algebraic group. So from now on, the equations are defined over K and not C, but we'll see that in 2 seconds that it will not be a problem because the Qi are defined over C. So let me write. So the alpha, PEG alpha, and the D alpha from a basis of the C vector space from so it's from the alpha are element of K and from a family of C linearly independent element. And PG alpha are half coefficient in C. And we are done because the PEG alpha define the Galois group. So in other words, you are in the Galois group if and only if you cancel every equation. So We will see further some example and how to compute this Galois group. So we have seen that the Galois group has a structure of algebraic group, and let me give you some other properties that will be very useful in the circle. So I will not make many proofs in that section, but I will state some useful facts. So the first one is the change of variable. Or we say a Gauss transformation. So it's a very easy computation to show that if you change your variable y by your variable z with equals to b times y, so you can compute an equation with respect to b to z. So it's sigma of b times y. So it's sigma of b, sigma of y. So it's equal to sigma of b and sigma of y equals ay. And now I multiply by b minus 1 to walk over. So we have seen that sigma of y equals ay is equivalent to sigma of z equals to sigma b a b minus 1 times z. So this formula will be very important in the following theorem. So so consider the case of sequences of shift or malware. So we can extend to Q and the elliptic case by taking a bigger K. So it's a detail and not important. So just focus on the case we know to treat. So let J be the Galois group. Let H be an algebraic group such that the matrix belongs to A of K. So it's just, this notation just means that you take the K point of H. So for instance, if H is SLN and K is C of Z, you just say that A is a matrix having coefficient in C of Z with determinant 1. Okay? So the first thing is that there is this B, there is this Gauss transformation such that sigma of b a b minus 1 is a K point of G, and the second one say so you can take a Gauss transformation that would put your matrix inside J. And the second one is that if C minus C of B A B minus 1 it's an hash prime point of K, where hash prime is an algebraic group. Then J is included in H prime. And the last statement, I will make an example soon, is that J over J0 is cyclic. And J0 is the connected component of the identity. So, for instance, just to give an intuition of the notion. So take the case S, so K equals C of X, and if H is equal to SLN, so H of K is just SLN of C of X. So it's just a matrix having coefficient determinant 1 and coefficient in C of Z. And imagine that, so let me take n equals to. Imagine that J is following a group. So it's an algebraic group. Then it just means that there exists B in SL2 of C of X, such that you can transform your matrix into an upper triangular matrices, and alpha belongs to C of Z. So this theorem just say that you can transform your system into something very small, which is a Galois group, and less relation you are able to make appear with respect to the different coefficient of your system, smaller is the equation. So it's a game to try to make appear more and more relation among the coefficient of your matrix. So in some sense, the Galois group is minimal in sense of Gauss transformation. And so this, as we will see in the next chapter, this is very useful to compute the Galois group. So now let me state the Gerard correspondence. So remind that you have a structure of direct sum of integral domain. So I may consider the field of fraction of the R tilde I. And I may consider the direct sum of Ki. Okay. So it's a direct sum of field, and K is the total field, the total PV ring. So it's a total field of projection. And you have a very fundamental result that say that the dimension of the Galois group, so seen as an algebraic group, so the dimension of a C of the Galois group equals to the dimension as a K vector space of each of the Ki. So it means that the Galois group really measures the solution, the algebraic relation between solution, and bigger is your Galois group and less relation you have. So for instance, if J equals to SL2, so dimension of SL2 equals 3. So you have 4 indeterminates and you have one relation, so it's 4 minus 1. I will not define very precisely what is the dimension of an algebraic group. It's a notion that is quite classical, but not so easy to define properly. It's just what you think. And so it means that if you have a fundamental solution, then there is at least one relation between the ZEG. Okay, and now I am ready to state the Gerard correspondence. So assume that K is a field. So it's just to simplify. So the Gerard correspondence also hold in the general case, but I just want to write it in the simple way as possible. So let big F. So it's the intermediate field extension, the intermediate difference field extension. So J it's the algebraic subgroup. So it's subgroups that are algebraic group of the Gerard group. And let me define two objects. So gal of K over F, it's so the element of the Gerard group might be extended to element through ring automorphism of K just by taking the quotient. So it's the element of the Gerard group such that P with respect to F is the identity, and K of H it's the element that fixes every element of H. And then I can define two maps. So alpha from F to J, and you take F and you map gal of K over F, and beta, and you go from J to F to H, you map K of H. So the two maps are each other inverse. So in other words, you have a correspondence between the subgroup and the subfield. So if K is not a field, it's a little more complicated to define the map F, but you can do it. It's possible. I refer to the course of Singer if you want, to the precise statement. And as a corollary, we can prove the following fact: that if A is fixed by the Galois group, then A belongs to K. So it's very important. It means that an element in the total Picard-Vector extension that is fixed by the Galois group is an element of the ground field. So I think we made sufficiently theory. So let me treat the example of the gamma function. So let me start by an example, by the exercise. So you have a structure of Galois group, and the structure forces a lot of relation. So it means that you have very few possibilities of such a relation. And to emphasize, I will consider the order one equation, where there are very, very few groups that may appear, so very, very few relations that may appear. So first one, the classification of the groups that I leave as an exercise. It's not very hard. So I consider an algebraic group. So of course, GL1 of C, it's isomorphic to C star. And we have to show that either G is C star, or there exists N such that J is just a complex number, the n root of unity. So it's not hard to see that both are algebraic group, so C star and the root of unity is algebraic group. It's a little more complicated to prove that the converse is also true. So it's a hard exercise. So I put a star here to show that it's an hard exercise. But it's worth to do it. And now, so as an example of gamma function. So we are in the framework S, and gamma function is solution of this equation. So we want to prove that gamma is not algebraic over C of X. So gamma is algebraic if and only if there exists P having coefficient non-zero, not zero, such that P of cancel gamma. So to the contrary, assume that gamma is algebraic. So I consider R tilde Picard sur extension. So as again I is a maximal sigma maximal ideal. So let gamma tilde is the image of gamma inside R tilde. So since gamma tilde is so since gamma tilde is algebraic, it means that since gamma is algebraic, it means that gamma tilde is algebraic. And so it means, sorry, it means that the dimension so again I call I take the decomposition. So it means that the dimension has to be 0. So since every element are algebraic, so the dimension of so there are no transcendental elements, and it means that the dimension of the Galois group is 0. So it will help us to compute the Galois group. So it's a subgroup of GL1 of C. So with the exercise, it implies that there exists n. So it cannot be C star. So there exists n such that may be seen as a complex number as a primitive root of unity. Okay? So Now consider psi in the Galois group, and let me compute the following elements. So it's so the n commute, so it's C of gamma tilde of power n, and since the element are the primitive root of unity, it's equals to psi of gamma n. Sorry, it's not psi of gamma n, it's gamma n. So it implies that it is fixed by the Galois group. And by Gerard Correspondence. It implies that it belongs to K, which is in that case C of X. Okay, but sigma of gamma tilde n is equal to x power n times gamma tilde n, and I leave as an exercise the following fact. There are no f in C of x solution of f x plus 1 equals to x to the power n times f of x. So it's not very hard to say that. You just have to consider the pole and the zero, and you will see that you will conclude. So we find a contradiction. And gamma is transcendental. So to summary, the fact that there is a structure of algebraic group, this implies that very few relation may appear between the solution. So it's the first step, and the first step is that we may convert this relation with relation between the coefficient. Of the equation. So it's a general method that does not work anytime, but that may work in some times, and we will see that for order 1 and order 2 equation we can do a lot of things. So that's all for this chapter.